Hello, this is Mr. Sorrentino again, presenting you another video in this Math 31 series of lectures. And this one is going into 4.3, which deals with polynomial division, the remainder theorem, and factor theorem. Ultimately, one of the main things we're trying to do in this chapter 4 is come up with methods of helping you solve polynomial equations, namely finding the zeros of polynomials. Because if you solve it, if you change any equation that's a polynomial equation and set it equal to zero, that's all you need to do to solve any polynomial equation. Um, we looked at some graphing things that helps us like kind of get an idea what the graphs look like, which could help us identify where zeros may or may not be. And so we've looked at those techniques, but there's still some things that were missing from it, and then that, even when we did an example of a graph in the previous video, although it was very close, it wasn't, as accurate, because as I noted on that graph, I kind of had it drawn with the minimum occurring at 0, -8, and that's not where the minimum actually was. So there might be more things we need to look at as we do this to help determine what the shape looks like and come up with an accurate graph. But ultimately, to do that, we're going to have to find ways of factoring polynomial expressions to find those zeros. And although in certain formats we can do that quite easily, in others it's not as easy. So we're going to look at methods here of helping to identify and determine where factors and therefore zeros may be, and use that and add that to the techniques we've used so far to come up with better graphs and come up with solutions to these polynomial equations and functions. And one of the things that we can make use of for this is the factor theorem. And what this factor theorem allows us to do is if we're able to somehow identify the zero of a polynomial, then knowing a zero helps us know what a factor is and vice versa. Because for a polynomial f of x, if f of c is 0, then x minus c is a factor of f of x. So that means if I'm able to use some technique of determining what the zeros of a polynomial are, I then know what the factor is. So for instance, when I look at f of x equaling x squared minus 6x plus 5, as it is in part A here, we have methods of factoring this. I'm going to use the AC method on this being A, the -6 being B, and the plus 5 being C. Because I notice here, because if I do AC, that equals a positive 5. And there's not a whole lot of factors that could come out and give you positive 5. As a matter of fact, there's only two. I could have 1 times 5, or I could have -1 times -5. And so, as we can see here, it's a -1 and -5 that when added together give me that -6. So I want to think of, doing this is that f of x would equal x squared minus x minus 5x plus 5. And then I could do a group and factor from there, grouping these two together and grouping these two together. And I can say, well, factoring an x out of the first group gives me an x minus 1. And if I factor a -5 out of the second group, I get an x minus 1, which in turn, since both of them have this multiplication in it, I could factor that out. And what's left when I do that, because these would go away, is x minus 5. So that's a basic factoring technique that we looked at before when we were factoring quadratics. But factoring, remember, doesn't always work. It only works when we have rational functions and, our rational zeros. The fact of the matter is just because I may have a situation where they're not rational doesn't mean I can't do this. So for instance, if I tried the AC method on this, uh, and I'll just show it really briefly, kind of up here. If I start with the AC method on part B, I have a 1 here, I would end up with 4. And the only ways I could get 4 are 1 times 4, 2 times 2, -1 times -4, and -2 times -2. None of those will add up to give me a -6, which is what B equals. Therefore, I cannot use factoring, quote unquote, as a way of doing with this. But I would need to come up with some means of maybe factoring this to find out what the answers are. So if I wanted to, and if I could, since this is quadratic, I do have other methods of solving this if it's set equal to 0. I can find the 0 and then just simply use this rule to make it a factor. So let's apply the quadratic formula. Because now if I set it equal to 0 and find the zeros, I could say, well, x is going to equal 6 plus or minus the square root of -6 squared, which is 36, minus 4 times 1 times 4 all over 2 times 1. I end up with the square root of 20 in here. The square root of 20 can be simplified or split up into square root of 4 times square root of 5, with the square root of 4 being the largest perfect square that goes into 20. And therefore, I would end up with 6 plus or minus 2 square root 5, all divided by 2. And if I divide by 2, remembering to distribute, I'm going to have 3 plus or minus the square root of 5, are my zeros. So my zeros are x equals 3 minus the square root of 5, and x equals 3 plus the square root of 5. Those are my zeros. These are zeros. Which means to find factors that would give me the x squared minus 6x plus 4, and let me scooch this up a little bit, all I really have to do is slap some x minuses in front of them. So the factors for B would be x minus 3 minus square root 5 and x minus 3 plus square root 5. And if I simplify these a bit by I don't like having parentheses inside parentheses, I could rewrite this and now say, well, f of x factored is x minus 3 plus square root 5 times x minus 3 minus square root 5. And so what I would have, this is almost written as a trinomial because, I'm looking at 3 plus square root 5 as a single number, but I'm writing it as a rational and irrational term combined. So this would be a way of factoring it that I wouldn't really be able to come up with using techniques from before. I could do the same thing with C. If I determine what some of the zeros are, I could easily figure out, how to factor it. Gets kind of hard to do because we haven't talked about some of the other things we have at our disposal that we're going to talk about in this lesson. So for the time being, I might have to use another method. And we've talked about other methods before. And one of the methods that we always try out is that if I have an even number of terms, which I do, I have 4 separate terms here, I could try a group and factor. I split these into 2 equal groups, and I look to factor the first group. So what will come out of the first group? it looks like basically an x will come out of the first group. Or no, an x squared. I kind of put over the parenthesis over the 1 squared. So I can factor out an x squared out of the first group and end up with 4x minus 3. And then I can factor out a negative 3 out of the second group and end up with 4x minus 3 as well. When I do a group and factor, I'm hoping that when I factor both groups, I end up with the same thing left in parentheses. It's not a guarantee. And so don't force it to happen if it's not meant to happen. It just means that this method won't work and we have to go on to something else. So sometimes you will try this and it will not work, and you'll have to resort to using another technique that we're going to talk about as we go through this lesson. So as a result, f of x can be rewritten as 4x minus 3 times x squared minus 3. Now that's factored, and if it's factored into linears and quadratics, we're typically happy. But if we wanted to factor this even further, I could say, okay, well, with this information and set this equal to 0, I can find the zeros. And the zeros of this polynomial would be occurring when 4x minus 3 equals 0, or x squared minus 3 equals 0. And if I solve both of these, this one here, I'm going to add 3 to both sides, divide both sides by 4. I get x equals 3/4. And on this side here, if I take x squared, I get 3, which means x is going to be plus or minus the square root of 3. So my zeros are x equals 3/4 square root 3 and negative square root 3. If I want to write this in a new factored format, say I have f of x equals, well, the 4x minus 3, as we saw here, is what gave us the x equals 3/4. So me rewriting the 4x minus 3 is the factor that gave that to us. The other two factors I can write, though, are going to be x minus square root 3, just putting an x minus in front of that, and x minus a negative square root 3, which of course is going to become a plus square root 3 if I simplify it further. So 4x minus 3, x minus square root 3, and x plus square root 3. And if I would take the time to go through and use the distributive property on this, I would get back the original function. As I said before, factoring it completely into linear functions is not always going to be necessary for our purposes. As a matter of fact, most of the time we're not going to do it. This would be suitable enough because we have methods of dealing with linear equations as well as quadratic equations. So as long as we are able to split a function into linear and quadratic parts, we're good. We don't necessarily have to go and make everything linear parts to do it. Factoring, though, it could be a little bit daunting because sometimes it's not as easy as using a group and factor. You may have to try and put some numbers in and see if they become zeros and factor that way. So we're going to talk about some ways of, once we establish that and maybe the grouping and factoring doesn't work, well, how would I get this factored? If I look at a function and I say I figure out that x minus 3 is a factor and the grouping and factor doesn't work for that, how do I find other factors? How do I, factor that x minus 3 out? Because we really don't have a procedure for doing that. if we can't use a group and factor and if we don't have quadratics to do it. So let's see how we would go about doing that. One way of factoring something out of, like a polynomial expression out of another, is to do long division. So let's look at long division first. So long division is aptly named. It is a long process. And you're going to see that as we go through and do this. But before we get into doing this for polynomial functions, let's review long division from your good old elementary school days where you learned how to do that. So before we get into doing this division up here, which I didn't want to write that, let's do a division over here. Say I wanted to divide, I'm just going to come up with some random numbers, 64, 71, and I want to divide it by 58. Pretty standard thing that you have to sometimes handle when you do this. Let's go back and talk about how we used to do this long division. Well, we always had the first number, the one that's being divided, go underneath of this bracket. It looks kind of like a square root symbol. Some people actually start using square root symbols for this. It isn't. But, you know, we use this. And the 58 would come out here. The next thing we do is we would start with the very first term and say, okay, well, how many times could 58 go into that first term? Well, since this is a two-digit number out here, 58 is not going to go into 6. So with the first term, if that's the case, then I would then look at the first two terms and say, okay, well, how many times does 58 go into 64? Well, 58 times 1 is 58. 58 times 2 is 116. That's way too big. So it seems as though 58 is going to go into 64 one time. So do 1 times 58 and get 58. I would subtract what was here. 64 minus 58 is 6. And once I got a number here, I would bring down the next term, 67. 58 does go into 67. Again, since 58 times 2 is 116, that's too big. It's going to go in once again. And 1 times 58 is 58. When I subtract these now, I get a 9 here. I bring down the 1. Now, I picked one, I was just picking one just to show the review the process. So obviously we have different numbers than ones than this, but this one here just happened to be that all were ones, because again, 58 times 2 is 116. That's way too big. And when I subtract this, I would end up getting 33. Now, after this point, what I would typically do is carry through. I mean, I'd either say, take this as a remainder. I would, or I would go and say, okay, I would do 111 and 33 58ths, and if I could simplify that, which I don't think I can, yeah, 3, 11, 2, and 29 don't have any common factors, so that would not simplify. Or the other thing you could possibly do when you had numbers is you would say, okay, I'm going to put a decimal point here and here, put a 0 here, drop that down here, and keep going with this until I either find a repeating pattern or it would terminate along the way. So I could sit here and say now, you know, 330 and say, well, 116 will certainly go into that now. I could try 3 times 58 and, you know, 4 times 58 and see what would possibly work with that and keep going with this. The remainder part is good for our purposes here because when we do these divisions eventually, you're not going to be given any problems where you're just asked to do the long division. You're asked to do the other type of division we're going to talk about momentarily. You're going to do the division for the sole purpose of factoring. You're not going to do it for any other reason. So you're not going to get situations where there's remainders because you're going to be using it for a very specific purpose. We're going to talk about remainders momentarily, but and more so in the next lesson. but we're not going to really focus our attention on what the remainders are and how we get to those. We want to focus our attention on the ones where we have no remainders, and there's ways we can figure that out. How does this work with a polynomial? Well, when I set up the long division for this, what comes first, much like this, is going to go underneath the long division sign. So the 4x cubed plus 10x squared plus. Now, one of the first things you have to realize, we're always going to have these written in standard form. So keep in mind that, first of all, the expressions will be written in standard form. Which means that if it's not written in a way where any of the expressions are going from highest power of x to lowest power of x, I'm going to change that. I'm going to make sure they're put in that order. The second thing I'm going to make sure I do is missing terms will be represented with 0 coefficients. And so what that means is, when I look at this expression so far, I have 4x cubed plus 10x squared. I don't have an x term. So I'm going to place that with a 0x, then a plus 9. This is the exact same thing. Typically, we don't write it with the 0x there. We would just simply ignore it. We need this for the placeholder because the position, the x cubed, x squared, x, and constant term are kind of describing that they're taking the places of the place value of the numbers. So if I don't have any x term, I need to signify that with a 0. Works the same way with the number out here. Out here I have 2x squared. I don't have a 0 term, but I have a minus 5. So I write it the same way, and if there's any missing terms, I put 0 coefficients in their place. I know since there's 3 terms out here, I'm going to be going 3 terms at a time. But I'm only mainly concerned about the first terms. So as a side problem here, I'm going to say, okay, well, 2x squared times what is going to give me a 4x cubed? Well, for the coefficient, I'd have to multiply that by 2 to get the x squared to become an x to the third. I'd have to take x squared times x. So I know that I had to multiply 2x squared out here by 2x to get the 4x cubed. I want that to match up. So I'm going to multiply by 2. I'm going to indicate a 2x up here. And then I'm going to multiply this entire thing by that 2x. 2x times 2x squared is 4x cubed. I wanted that to happen. I wanted that first term. It's always my desire to make the first term match. The other ones, if they match, so be it. If they don't, oh well. 2x times 0x would give me a 0 for coefficient x squared. Now again, under most normal circumstances, I wouldn't have had the 0x there to begin with, and even if I did, if I had up with 0x squared, I would tend to ignore it. But I'm not doing that here. I got to make sure to keep the places in line. 2x times a negative 5 is a minus 10x. Now, just like before, over here, I'm going to subtract. Now the thing is, I'm not subtracting a number here. I'm subtracting an expression. So I'm subtracting this entire quantity, which means I have to distribute the 0. So we usually don't write the parentheses there, mind you. Just when I put the subtraction in, I have to make sure that each term is being distributed. So basically that means that every term is going to have a sign change. So this becomes a minus, this becomes a plus. 4x cubed minus 4x cubed cancels. The first terms should cancel if you're doing this right. If other terms cancel as well, great. If they don't, that's okay. 10x squared minus 0x squared is 10x squared. 0x plus 10x is 10x. And then I bring down the next term like I had done with the other division, with the numbers. So I'm going to bring down to plus 9. Now I'm focusing my attention on this new first term. And I'm going to ask myself the question, 2x squared times what gives me 10x squared? Well, we know that there's no change in the exponent, so I'm not multiplying by anything that has an x in it. Therefore, the only thing that's going to change is the coefficient, and 2 times 5 equals 10. So 2x squared times 5 would be 10x squared, which means I'm going to multiply this now by a positive 5. And since it's the second term, I have to indicate positiveness by a plus sign. And so I'm going to get that 10x squared. 5 times 0x is 0x still. 5 times negative 5 is a minus 45. I would subtract. Again, when I subtract, it has to be distributed, so that's going to become a minus. This is going to become a minus. This is going to become a plus. These cancel. They should. 10x minus 0x is 10x. 9 plus 45 is 54. Now, at this point in time, as I said, when we do the divisions, it's not going to matter so much how we handle this part of it. I could say the remainder is 10x plus 54 because once I get a power of x that's below the divisor's power of x, I can't carry through the division anymore. There's some calculus explanations for that along the way, but I'm not going to get into those because you're not in calculus yet. We're just doing a course that's eventually going to help you get prepared for it. So I could just state like the answer is 2x plus 5 and the remainder is 10x plus 54. Another way I could state this answer, depending on the circumstance, and what we'll use more so as we get into talking about rational functions, is I could say that the answer would be 2x plus 5 plus 10x plus 54 over 2x squared minus 5. Much like the mixed number way of just taking the remainder that was there, putting in the top, and then putting the 58 in the denominator. Remember, there is a plus sign indicated in a mixed number, whereas in expressions where I have variables, that plus sign has to be more directly written. So either one of these would be acceptable answers for this. So that's a procedure for long division. Now, this one wasn't too bad because we started with an x cubed term. We were dividing by an x squared expression. The bigger the discrepancy between the two, the more work there would be when I do long division. So here, I had to do two different steps to do this long division because I was taking an x cubed term and dividing it by an x squared term, or an x cubed expression and dividing it by an x squared expression. In the next one, I'm taking an x cubed expression and dividing it by an x expression. So I have a degree 1 polynomial expression being divided by, or a degree 3 polynomial expression being divided by a degree 1 polynomial expression. The more of a discrepancy between those degrees, the more steps there are in this process. So let's look at the division of this over here, because this type of division is what's going to happen most frequently with us. And when we do various things in order to find zeros of polynomials, make graphs, and so forth. So let's scooch this over a little bit. And I'm going to do, let's put like a little wavy line over here to kind of separate them. And here I'm going to do, again, the expression that comes first is what goes underneath here. Now here I don't have any missing terms. I have an x squared and x cubed and x squared and x in a constant term, so everything there is good. Just have to copy it. And I have the x plus 3 out here. Again, no missing terms. I focus my attention on the first terms. And I have to ask myself, okay, x times what equals 2x cubed? Well, I went from having a coefficient of 1 to a coefficient of 2. So that means I had to multiply this by 2. I went from an x to the first power to an x cubed, so I had to multiply this by x squared. So for me to have that all happen, I had to multiply x plus 3 by 2x squared to get a 2x cubed in the same first position. So I'm going to carry through, I'm going to multiply 2x squared to x plus 3. It's distributive again. So I'm going to have 2x cubed plus 6x squared. And I have to remember now that I'm going to carry through the subtraction, so I'm going to subtract, but that subtraction gets distributed, so this becomes a minus as well. These cancel. Negative 2x squared minus 6x squared becomes a minus 8x squared. And I bring down the next term, which is a minus 7x. And now I focus my attention on this new first term. And so I have now x times what would give me a minus 8x squared. Stands to reason negative 8 should be part of that. To have x to the first become an x squared, it had to be multiplied by x. So I had to multiply this x outside by a minus 8x squared. Or minus 8x, sorry. And so I'm going to have a negative 8x squared minus 24x. Again, I'm going to carry through the subtraction. Since I'm going to be subtracting, this becomes a plus because it's going to have a sign change, minus a negative, and same thing with this. These cancel. Negative 7x plus 24x becomes 17x. And I bring down the 15. Now, when I do this now, it's going to be my last one. I'm going to have a remainder after this. So again, my new first term is 17x. I think again, well, x to the first power times what gives me 17x, technically to the first power. Well, the powers remain the same, so there was no x in whatever I multiplied it by. I just had to make the coefficient go from a 1 to a 17, so I know I had to multiply this by a positive 17. That's an ugly x I had up there. Plus 17. And so I'm going to add up 17x here plus 17 times 3 is 51. I carry through my subtraction. These cancel. This is a minus now. 15 minus 51 becomes a minus 36. And that's what the remainder is. So I end up, so if I divide, I'm going to end up with 2x squared minus 8x plus 17 with a remainder of negative 36, which is kind of different because long division with numbers, we didn't have negative remainders. Here we're going to, and that's, that's another new thing about this. That was kind of lengthy. Now, if I had had a situation where I had like a 6th degree polynomial expression being divided by a 1st degree one, that'd be even more steps. None of them particularly difficult, but just time consuming. So, and it's this kind of division where I'm dividing by what we call here a linear binomial. with a leading coefficient of 1, that's going to be the circumstance that whenever I start wanting to factor these polynomial functions, that I'm going to have, because chances are I'm going to probably be able to find a 0 or 2, change them into a factor by putting an x minus in front of them, and therefore I'm going to have x minus some number or x plus some number because I had x minus a negative. And then, that's what I'm trying to divide out and see what I have left to possibly factor some more. So this is the kind of situation I'm going to be happen most often because, of the rule we had before about how to use the factor theorem. So this, being so time consuming could be a problem when I'm trying to do this rather quickly. So we have another method of carrying through this division. And you're going to see we're going to get the exact same answer and result that we would do if we're doing the long division. So let's have a look at synthetic division. Now notice in example 3, I have this exact same thing as I did in example 2, part B. But here's what's different about it. I'm going to take what's inside the first quantity, the first expression, the one with the higher degree. And all I'm going to do is write the coefficients. So these, gotta switch back to my pen, these are the coefficients of the dividends, which I think they officially call the number being divided. So, I have a 2, minus 7, and a positive 15 here. That's what I have here. This number is the 0 of the divisor. Since x plus 3 is the expression, I got to think, well, what number would make that a 0? Well, negative 3 would. So that's what goes here. And then once I have this set up, how I carry this through is as follows. I start with this number up here, I bring it down below the line and just say 2. To create a new number that goes right here, I'm going to multiply the negative 3 I have in this half box to the left, upper left, times this 2. So I'm going to do negative 3 times 2 and get a minus 6. I'm going to now, and here's what's another major difference, I'm going to add these two together. So negative 2 plus negative 6 is a negative 8. Once I get a new number down here, I'm going to now multiply that by the negative 3 up here. I'm going to get a plus 24. I really don't need to put a plus sign there, but I am going to add the numbers together, which gives me a positive 17. With the new number down here now, I'm going to take the 17 times negative 3, I'm going to get a minus 51. And when I subtract, I'm going to get a negative 36. The number that ends up in here is the remainder. As I work my way this way, this is my x to the 0 term, or my constant term. This is my x to the first term. This is my x squared term. If I had more, it'd be the x cubed term, the x to the fourth term. So based off of this, the answer is 2x squared minus 8x plus 17 with a remainder of negative 36. And as you can see, that does work a bit faster than the long division did. Again, synthetic division only works when you are working with a linear binomial, and I'm going to make sure to emphasize here, and leading coefficient of 1. It gets a little bit more complicated if you don't have that. So, that's a shortcut. Now again, we're not going to be using this synthetic division for just doing division. You're not going to say, hey, divide this. You may have some practice problems in your textbook just to get you used to the procedure, but ultimately the goal is not to use synthetic division just to divide two polynomials. It's going to be used once you know that the remainder is going to be 0. You just want to use it to break down the function more. So if you're able to establish a 0, then you could turn that into a factor, carry through the division, and then you have it broken down into that factor times whatever's left over when you carry through the division. For this to be useful as well, we're going to talk about now the remainder theorem. So let's talk about the remainder theorem and what that tells us. So we're going to do an exploration of the remainder theorem. And I'm going to be doing these using synthetic division just for the time being, because we're going to hopefully notice something that goes on with this. So we know that f of x is being defined here as x squared minus 6x plus 7. So in the first one, I want to do f of x divided by x minus 7, which means that for a, I'm going to be taking the function f of x, which has coefficients 1, -6, and 7, and I'm going to divide that by a 7, because that's what the 0 would be for that factor. And I'm just going to carry through the synthetic division here. So, and I'm not going to do this, I'm not doing it in fast motion here because this gives us an opportunity to practice more synthetic division. So as I carry this through, bring down the 1, multiply that by 7, I get 7. -6 plus 7 becomes a 1. That should be a minus 7 up here. 1 times 7 is 7, and I get a remainder of 0. So the answer to this is, so this is basically telling me I have a remainder of 0, and this is my constant term. It's a constant. This is my x term. So this division is equal to x plus 1 with the remainder of 0. When I do b and do f of x divided by x plus 2, I'm still going to have the 1, the -6, and the -7. Since x plus 2 is the factor, the 0 that would result from that is a -2. And so if I carry this through, bring down the 1, multiply by -2, I get -2. Add those together, I get a -8. Multiply that by -2, I get a 16. -7 plus 16 is 9. This is my remainder. This is my constant term. This is my x term. And so that means when I carry this through, I end up with x minus 8 and a remainder of 9. But let's see what happens now. What if I just did f of 7? Notice that, 7 is the 0 that becomes this factor. If I do f of 7, I'm going to have 7 squared minus 6 times 7 minus 7, which is 49, minus 42, minus 7, which equals 0. That seems to be the same remainder. And it stands to reason. If 7 is a 0 of this polynomial, by the factor theorem, I would expect x minus 7 to be a factor. And if it's a factor, and I carry the division through, for it to be a factor, I get a remainder of 0. Going back to numbers, 2 is a factor of 12. How do I know? When I do 12 divided by 2, I get 6 with no remainder. So that's how I know it's a factor. Here, again, this -2 is the root I would get from this factor. So there's a relationship between this. This is the factor for this 0. What happens when I do f of -2? Well, if I plug that into the function, I'm going to have -2 squared minus 6 times -2 minus 7. That's 4 plus 12 minus 7. And 4 plus 12 is 16, minus 7 is 9. It matches yet again. So I don't have to carry through a division to figure out what the remainder is going to be when all is said and done, as long as we're talking about linear binomials with a leading coefficient of 1. And that's what the remainder theorem has you notice, and that's what it basically states. Given a polynomial f of x and the division of f of x divided by x minus a, of course, binomial, 2 terms, linear because x has a power of 1, leading coefficient is 1. Has a remainder r if and only if f of a equals r. So basically, if I want to figure out what the remainder is, all I have to do is plug in the number, the potential 0 I'm going to have from the factor, and it's going to tell me what the remainder is. That works for these linear binomials, and that's the whole reason why the factor theorem works. A 0 of a polynomial is going to be it's going to help me figure out what a factor of the polynomial expression is going to be. So these two working together is what allows us to, well, if I can find some zeros, that helps me factor, and it might help me find other zeros. Because even though we may have a graph in front of us, that graph, might not give us the exact value of irrational factors. I mean, if I even use my calculator, I might get some decimal. It's an approximation. If there's some non-real factors or non-real zeros, they won't even show up on the graph. And I need to be able to find those too, and I'm expected to know how to find those as well. So that's what we're going to start looking into. How are we going to do this type of thing? So let's look at example 4. Now this is kind of getting into a situation where I'm using the calculator. I really don't have to use the calculator on this. If you look, you could use a group and factor method of finding for factoring this and breaking this down in much the same way. I'm setting it up this way so that you can see how the calculator could be useful in identifying some zeros, and 2, how it's going to help me eventually get the exact values of some of the other zeros. Now, I'm not going to show this all on the calculator because I have pictures that are from the notes in here as well. So here you're asked to find all the zeros. And you're asked all the zeros, and you're asked to find exact values. That exact values is very important because, if I just said find the values of the polynomial, you could, potentially find the answer to this just by graphing it and using your trace functions and things of that nature. So what you're seeing here is this is a graph of y equals x cubed plus 2x squared minus 10x minus 20. And you can see what the settings were for us to see what we have here. As you can see, this graph does show 3 zeros. And that's how many zeros I expect. I don't expect any more. Because I'm already seeing those 3 zeros, because the end behavior should have this pointing left on the left, pointing down on the left-hand side and pointing up on the right-hand side, I know I'm having a sufficient graph here to determine that I have all my zeros in front of me. So I'm using those facts that we've mentioned in previous lessons to establish that, yes, these are the only zeros I expect to see. Now, if I'm using the calculate menu, I find out, as this mentions here, this is my x equals -2. This number here is -3.162776, and that's rounding. There's no repeating pattern to this, and it doesn't just terminate. Usually termination, you're going to see like -3.25, bam, done. Or you might see it as negative 3.24999999, so it indicates that you would normally just round to 3.25. This number here, the way it's coming up on my calculator when I use the calculate menu, indicates that this is irrational. Same thing with this. It's just a positive version of this, which stands to reason we talked about before that irrational roots or zeros tend to come in pairs. The problem is, if these are irrational and I have these decimals, this is not the exact solution. That's what this wavy equal sign means. It means approximately equal to. I don't want approximately equal to. I want exactly equal to. So I got to try to figure out what this number is written in exact form. And the only way I'm going to be able to do that is to break this down and try to solve this situation. So I am solving a situation where this is set equal to 0. I know from this that x equals negative 2 is a 0, which implies that x minus negative 2, which of course is the same thing as x plus 2, is a factor. Since I know it's a factor, I should be able to divide it out, get another expression, that's the quotient, that has a remainder of 0. So essentially, I'm doing this synthetic division now to factor this. Because right now it's a cubic function. I don't have methods of solving this equation for cubics. But if I can break this down into factor out this linear factor, I'd end up with a quadratic one as well. And I can solve quadratics. I can find zeros for quadratic expressions. I can't find them for cubics. So I'm going to carry through the synthetic division now. So again, the synthetic division, I have it set up. So, here's my coefficient of 1, which goes with the x cubed, the 2, which goes with the 2x squared, the negative 10 goes with the minus 10x, the minus 20 that goes with the minus 20. And of course, in synthetic division, I use the 0, not the factor. So that is a negative 2. So I do the synthetic division. I bring down the 1. Multiply that by negative 2, I get negative 2. I add the two numbers together, I get a 0. Negative 2 times 0 is 0. Add those together, I get a negative 10. Now I multiply the negative 10 times negative 2, I get a positive 20. And I get a remainder of 0. Good, I should get a remainder of 0. This is my constant term, this is my x term, this is my x squared term. So obviously when I rewrite this, I don't have to write the 0x. I can get rid of that as part of my solution. So now I know that f of x, originally written like this, can be rewritten as x plus 2, because that's what gave me the negative 2 as a 0, times x squared minus 10. And I'm trying to set that equal to 0. The zeros, therefore, well, we already established that negative 2 was a 0, but if I go through the process I normally do at this stage, I'm going to say, well, x plus 2 would have to equal 0, or x squared minus 10 would have to equal 0. Well, if x plus 2 equals 0, we get that x equals negative 2. That's not a shocker because we've established that much earlier in this problem with the calculator. Or I could have even established that using group and factor. The x squared minus 10, this is going to be what generates that 3.16 something or other, and the negative 3.16 something or other, because I'm going to add 10 to both sides, and then I'm going to square root both sides. Remembering the plus or minus sign goes there. So I'm going to end up with x equals plus or minus the square root of 10. Those are my other two, because remember, one's the positive one, the other one's the negative one. So my zeros are, I could do them as a list. I could say it's -2, square root 10, and negative square root 10. Those are the zeros of my polynomial. And that brings us to the end of this video for section 4.3. Again, if you have any questions with anything discussed here, then make sure to bring them up in class or ask them about them in office hours. Until I see you in one of those locations, or until the next video, I will see you around. Have a good day, and I'll see you then.